Welcome to A-Level and AP Physics. In today's lesson, we will discuss all possible graph questions from alternating current topic. And we will discuss these questions in detail so you can improve your conceptual understanding of this topic and also you can have better understanding of graph questions. Let's study together. Let's improve together. Question 1 says, an ideal transformer has 5000 turns on its primary coil. It is to be used to convert a main supply of 230 volts RMS to an alternating voltage having a peak value of 9.0 volts. For part A, we need to calculate the number of turns on the secondary coil. So we can simply sketch a transformer here, the basic structure, so you can get better idea. So we have primary coil, so this is the primary coil and this is connected with alternating power supply. Transformer only work with alternating power supply. So it has primary voltage VP and it has number of turns on the primary coil, we can say NP. And here we have the secondary coil. So this one is the secondary coil. We can also connect voltmeter here. So in this case we can connect voltmeter. So let's say we connect over voltmeter here. So this is over voltmeter, and reading on this voltmeter we can say this is Vs, and the number of turns on the secondary coil we have Ns. This is what we need to find out. Primary voltage is given to us, but primary voltage, this is RMS value. It is given to us, this is 230 volts, that this one is RMS. We can say this is RMS. And Vs is given to us, this is the peak value. So we can say this one is the peak value and this is equal to 9 volts. And number of turns on the primary coil we have, that is equal to 5000 turns, number of turns. We need to find out Ns in this case. So for this purpose we need to understand the ratio between Vp over Np. This is transformer equation. This is equal to Vs over Ns. Now we need to find out in this case Ns. So Ns simply will be equal to Vs times Np divided by Vp. Now here problem is that this value is the RMS value and this is the peak value. So you cannot use two different values. You have to convert this one into RMS. Both of them has to be in RMS or both of them has to be in peak value. Means both of them, they should have peak values or they should have RMS values, but in this case we will convert into RMS values. So we have V peak, so we can convert this one into VRMS. So simply we need to divide this one by root of 2. So this is the RMS value. Now we can plug in values. Vs, we have 9, this is divided by root of 2, and we have Np, that is equal to 5000, and we need to divide this one by Vp, that is already RMS value 230. Now if we solve this one, our final answer will be equal to 138. So these are the number of turns on the secondary coil. So the key concept is that you have to use both values, RMS values or peak values. Part B says the output from the transformer is to be full wave rectified. Figure 4.1 shows part of the rectifier circuit. On figure 4.1 we need to draw the diode symbols to complete the diagram of the rectifier such that terminal A of the resistor is positive with respect to terminal B. Means this terminal has to be positive, so current has to enter from this side. Positive means that current has to enter from this side, and negative means that current will be leaving from this side. Now we need to draw symbols of diodes to make a rectifier circuit, or simply we can say bridge rectifier for full wave rectification. This side is positive, this terminal is positive and it is connected with this end of this diamond shape. So this has to converge. Diodes have to converge at this point, and from this point diodes have to diverge. Diverge simply means that the diodes have to be like this. Diode converge means they have to be like this at that point. So here they have to diverge, so simply we can draw the symbol here, a symbol of diode. So this is typical symbol we use for diode, and here they have to diverge, so this is representing they have to diverge, and here they have to converge to this point. So we can draw these diode symbols like this, converge, and here again they have to converge to this point because this point end is connected with positive terminal of the resistor, converge. So this is how you need to draw, but we can also check is it correct or not. Let's try to use a different color. When this side of power supply become positive, this side become positive, so current in this case will flow like this. Current will go like this. At this point current has two ways to go, down or this way, but current will not go this way because this is in reverse biased. So this is in reverse biased, so current will not go this way, but this is in forward bias, so current will flow this way. So we can say this is in forward bias, so you need to understand these terms as well. And so current will flow like this, but current cannot go this way because this is in reverse bias, so current will go this way and current will enter from this end. So this is positive terminal of resistor. Current will flow through this one. Then when current reach at this point, current has two ways to go. It can go this way or it can go this way, but current cannot go this way because this is at high potential. This is connected with positive, so the current will go towards low potential, so it will go this way. So this is how current will flow when the upper side of power supply is positive. After half cycle, this side will be positive. So let's use different color and see whether this is right or not. So we can use pink color now. So when this side become positive, this side positive, here current will flow like this. So let me use a better one, orange one, so that will be easy to see because pink is not that much clear. So we will be using orange one here, orange. So when this side is positive, current will flow like this, and when current is at this junction, it has two ways to go. It can go this way or it can go this way, but current will not go this way because this is in reverse bias, so current will not go this way. Current will flow through this diode, and again current will not go this way because this is in reverse bias for orange one, so current will enter from this side. So again you can see it is entering, so this is positive terminal. Then current will pass through this one, and when current reach this junction, current has two ways to go. One, it can cross this one, but this point, this is at high potential as compared with this one, so this is at low. So current does not flow from low to high, it flow from high to low. So current will flow this way and will pass through this diode. Again current will not go this way because this is at a higher potential, so current simply will flow like this. And so it means that our diagram is correct. This is correct diagram. If we go to the second part, we need to draw the symbol for a capacitor connected to provide smoothing of the potential difference across the resistor capital R, across this one. So for this purpose you need to understand, when you connect capacitor for smoothing, it has to be connected in parallel with the component. In this case component is resistor, so we have to connect this one in parallel with this resistor. So this is how you need to draw this diagram. I have explained you this one in detail. Now simply let me show you the answer, what you need to do for the answer of this question. So this is how you need to draw the answer for this question. I mean, these symbols you have to draw. This is how you need to draw, and I hope this one is clear to you. And this question is a typical type of question. Once it is clear to you, then it's a fun to play with full wave rectifier circuits. Part C says figure 4.2 shows the variation with time t of the smoothed potential difference V across the resistor capital R. For part C1, we need to state the interval of time during which capacitor is being charged from the transformer. So we need to understand when capacitor is charging, it means the smoothed potential difference will increase. So simply we can say smoothed PD increases when capacitor charges. So this is the point you need to understand. Capacitor charges. Now if you look at this interval of time from here to here, potential is increasing, so it means capacitor is charging here. So we can say this region is representing charging. And if you look at the next one, potential is decreasing, so this potential is decreasing. So this region, this is discharging, so this is discharging. So we can say charging, this is discharging, this is charging, this is discharging, this is charging, and this is discharging, and this part is also discharging. D for discharging. So we can write down any time interval. We can write down t1 to t2. We can write down there is no any other interval because this time is not given to us. So simply we can write down in this case from t1 to t2. So this is how you need to answer part 1. For the second part, it is given to us the resistance of the resistor capital R is doubled. On figure 4.2, sketch the variation with time t of the potential difference V across the resistor. So we need to re-sketch if resistance is double. So we need to understand when the resistance is double, the tau, the time constant, so RC. So if resistance is double, capacitance of capacitor is the same, so the tau of the capacitor will increase. If tau of the capacitor increase, it means capacitor will discharge slowly. Capacitor discharges slowly. So capacitor discharges slowly. So this is the point we need to understand. Capacitor discharges slowly, but time period of AC is the same. Time period of AC is the same, only tau for capacitor increases. So in this case, simply we can draw at this point capacitor will discharge, but it will discharge very slowly. So let me redraw this one, so we can redraw. Capacitor will discharge very slowly, so it will discharge slowly. So here it will charge, then again it will discharge, and again it will charge, and again it will discharge, and again it will charge, and again discharge, and so on. So this is how you need to sketch. Part C says a capacitor is now connected between the terminals AB of the output. The capacitor reduces the variation in the output to 1.6 volts. For part C1 on figure 11.2, we need to sketch the variation with time t of the smoothed output voltage for time t is equal to t1 to time t is equal to t2. First of all, before connecting capacitor, the variation in PD across a resistor is equal to 5.6 volts. Actually, if we draw the line here, we can see this is equal to 5.6 volts. And after connecting capacitor, we can say delta V, the variation in PD. After connecting capacitor, this is only 1.6 volts. So it means that we can draw a line 1.6. So 1.6 means 5.6 minus 4. So we can draw one dotted line here. 5.6 delta V 1.6. It simply means that PD is changing between two values. It is changing between 5.6 volts and between 4.0 volts. So the maximum is this one and the minimum is 4. So maximum and this one is minimum PD across resistor. Now we need to sketch the curve. So it will reduce when capacitor will be discharging. PD across resistor will decrease to this value. Then capacitor will charge. PD across resistor will increase. It will reach 5.6. Then again it will discharge to 4.0, and then again it will increase, capacitor will be charging, and then capacitor will discharge, so PD will decrease to 4.0, and then it will increase because capacitor will be charging, it will reach maximum value of 5.6, and then again it will discharge. Actually we just need to sketch until here from T1 to T2. So this is T2. T1 means from this point to this point. And so this is how we need to sketch. So we can clear this line, we don't need this one. This is how you need to sketch for the answer of this question. Let me show you the better one. So this is a better one, a proper one. This is how you can sketch. So let me clear this. So this is how you need to sketch. Now if you go to the second part, for the second part we need to suggest and explain the effect, if any, on the mean power dissipation in resistor capital R when the capacitor is connected between terminals AB. So the power dissipated, this is equal to V squared divided by R. So in this case, the first case, before we have the maximum value, we can calculate V average. V average, we have 5.6 minus 0 divided by 2. So this is the V average. V average, and after we have the V average, that is 5.6 plus 4.0 divided by 2 V average. So we can see after the mean PD across resistor, it has been increased. So this is the mean PD. If this value has increased, it means the power dissipated in the resistor, that one has been increased because resistance of the resistor is not changing. So simply we can say, as mean PD increases, as mean PD, we can write down this one in a proper way, as mean PD increases across the resistor. So this one is greater than this value. As mean PD across resistor across R increases, so mean power dissipated, we can say, so mean power dissipation greater, or we can say higher. So that's all what we need to write down for the answer of this question. This question has 2 marks. If you have mentioned these 2 points, you will get 2 marks. Question 11 says a bridge rectifier contains 4 ideal diodes A, B, C and D as shown in figure 11.1. The output of the rectifier is connected to a load capital L of resistance 2.4 kilo ohms. On figure 11.1, mark with the letter capital P the positive terminal of the load. So we need to mark the positive terminal of the load, means of this resistor. Positive terminal is the side through which current is entering. That side is positive terminal, and that one we can find out by just looking at this arrangement of diodes. So you can see at this side the diodes, they converge. So I can say diodes converge. So this is C. And if we look at this point, from here diodes, they diverge. So we can say this is D. And the C is connected with the load at this terminal. So it means this terminal is positive and diverging side is connected with the load here. So this side has to be negative. So simply we have to mark positive and negative. You can even check with the current. So we will check once. Let's say when this is positive, half of the cycle. So how current will flow? Current will flow like this. At this point, current cannot go this way. So current will pass through this diode because this is in reverse biased. So current will enter from this side. So this is positive. We can also check when the lower side is positive. When this side is positive, current will flow from here. It will go this way. But at this point, current cannot go this way because this is in reverse bias. So current will pass through this diode and again will enter from this side. So this is positive terminal of this load resistor. So this is how you need to mark. I have explained you in detail, but if you have understood this point, so simply you need to look the side are the point at which diodes converge, and that side is connected with positive terminal. So this is positive, and the point at which diodes diverge, that one has to be connected with negative. So this is how you can draw. For this question, simply you need to mark this positive and negative, means positive terminal you can mark with letter P. So this is simply you need to write down. Part B says the variation with time t of the potential difference V across the input to the rectifier is shown in figure 11.2. We need to calculate the root mean square value of current in the load, capital L in the load. So we need to calculate IRMS. So we can simply write down here is IRMS. IRMS has to be equal to VRMS divided by resistance of resistor. But in this case we can simply read the V peak. So here we have, this is V peak, we need to calculate VRMS. So we have to divide this one by root of 2 and we need to divide by resistance of resistor. V peak we have 6, this has to be divided by root of 2 and we need to divide by resistance of resistor, and resistance of resistor in the previous part was given, that was equal to 2.4 kilo ohms. So 2.4 kilo ohms. Now simply we need to solve this one. If we solve, we will get this is equal to 1.8 times 10 to minus 3 amps. So this is our final answer. Pretty straightforward question. Part C says the potential difference across the load capital L is to be smoothed using a capacitor. For part C1 on figure 11.1, we need to draw the symbol for a capacitor connected to produce smoothing. So we need to connect capacitor across load resistor, and that has to be connected in parallel with resistor. So here this is how you need to draw symbol for capacitor. It has to be in parallel with this load resistor. Very common question, so you have to understand where to draw symbol for capacitor. Capacitor has to be connected in parallel with load resistor. Second part says the minimum potential difference across the load capital L with the smoothing capacitor connected is 3.0 volts. On figure 11.2, sketch the variation with time t of the potential difference across the load capital L. But if you look at this given curve, this is not rectified. This is pure AC signal from the AC power supply. And also we need to understand the minimum PD across the load resistor is given, that is equal to 3.0 volts. So first of all we can draw the line here. So we have 2, 4, this is 2, so 3 is between them, 1, 2, so 3 is somewhere here. So we can draw the dotted line first of all. So this is the dotted line. As this is not rectified, so we can assume this is a rectified. So we can draw rectified curves, and also we can draw this for the peak value. For the peak value we can draw one from here. This is also for the peak value, so we can draw here. This will help us to draw the curve in a nicer way. Now we can assume this is rectified, so we can draw this dotted line. This is rectified, so this is rectified signal, dotted. This will help us to draw the curve. Now we can draw the curve. So you need to understand here power supply PD is decreasing, so the capacitor in this case will discharge. Capacitor will discharge up to 3.0 volts. Capacitor will discharge up to 3.0 volts, and then from here capacitor will charge up to this point, and then again capacitor will discharge here, and at this point capacitor will charge again, and then again capacitor will discharge to 3.0 volts, and then capacitor will again charge, and then capacitor will again discharge to 3.0 volts. So the last one we can draw again, the last one, because this is not good looking, so we can draw in a nicer way. So this will discharge to 3.0 volts, and again this will charge, and again discharge, like this. So this is how you need to draw. But in the exam what you need to draw is simply you need to draw this blue one. Rest of the things are just for your understanding. If I want to show you the curve you need to draw, this is the curve you have to draw, but the way you need to draw I have explained you in detail, and I also hope that this one is clear to you how to draw this one in a nicer way. A bit tricky question, maybe most of the students they will get confused with this one, how to draw on the AC signal, because most of the time in the exam they will ask you to draw on rectified signal. Question 10 says the rectified output of a sinusoidal signal generator is connected across a resistor capital R of resistance 1.5 kilo ohms as shown in figure 10.1. The variation with time t of the potential difference V across R is shown in figure 10.2. For part A, we need to state how the rectification shown in figure 10.2 may be achieved. So if you look at this rectification, first of all, we need to understand what kind of rectification is this one. This is half wave rectification, because half of the cycle there is no PD across resistor. So this is half wave rectification. So we can say this is half wave rectification. And half wave rectification simply can be achieved by using single diode in series with resistor. Single diode in series with resistor means simply if we can connect one diode here. So if we connect one diode here, we can achieve half wave rectification. Single diode in series with R. So simply we can say we have to connect single diode in series, with capital R. So we can say connect single diode in series with R. So if you write on this one, you will get 2 marks. Part B says a capacitor is now connected in parallel with the resistor capital R. The resulting variation with time t of the potential difference V across capital R is shown in figure 10.3. Part 1 says use figure 10.3 to determine the mean potential difference across the resistor capital R. So we can see this is the maximum value of PD. So maximum we can say V max. Maximum value of PD across resistor, that is equal to 6.0 volts. And we can find the minimum value of PD from here, minimum. And this minimum value of PD, this is 4.8. So we can write down V min. This is equal to 4.8 volts. And we need to find out the V mean value of PD, V mean. So this will be equal to 6.0 plus 4.8 divided by 2. So this is 10.4 divided by 2. So we will get 5.4 volts. So this is how we need to answer this question. For the next question, we need to calculate the mean current in the resistor and I mean in the resistor. So I mean, this is equal to V mean divided by resistance of resistor. V mean we have that is equal to 5.4 and resistance of resistor we have that is equal to 1.5 kilo ohms, means 1.5 times 10 to 3. And if we solve this one, we will get, in this case, this is equal to 3.6 times 10 to minus 3 amps. So this is the value of mean current. And if you go to the third part, the time in each cycle during which the capacitor discharges. So if you look at this given figure, from here we can see that in this part capacitor is discharging, mean here capacitor is charging. Capacitor is discharging between these 2 points. Here capacitor is discharging, and simply we need to write down this time, and also we can write down this time is the same. Capacitor discharging, so we can draw another line. You can also take this time. Capacitor is also discharging between this one. So here capacitor is discharging. You can say discharge, and here also discharge in this interval of time. And this interval is easy to find because this is 0 and this is 0.027. So simply you need to write down this is 0.027 second. So capacitor is discharging for 0.027 seconds. Part 2 says using your answers in one calculate the charge passing through the resistor during one discharge of the capacitor. So we need to calculate value of Q. Q is equal to I times T. We have already calculated mean value of current, so we have to use the mean value of current, and time of discharge, time taken to discharge. So we can say I T discharge. I we have calculated in the last part, that was equal to 3.6 times 10 to minus 3 amps, and value of time interval we have also calculated, that was equal to 0.027. Now simply we need to multiply and we can find value of Q. That will be equal to 9.72 times 10 to minus 5 coulomb. So this is our final answer, 9.72 times 10 to minus 5 coulomb. So this is how we can calculate. For the second part, we need to calculate the capacitance of the capacitor, and capacitance of the capacitor is equal to delta Q, means the amount of charge passing through the capacitor, divided by the change in voltage. Delta Q we have just calculated, that is equal to 9.72 times 10 to minus 5, and the change in potential across this capacitor, that is 6.0, means here we have 6 and here we have 4.8, minus 4.8 volts. And if we solve this one, our final answer will be equal to 8.1 times 10 to minus 5 farads. So this is how we can calculate 8.1 times 10 to minus 5. Part C says a second capacitor is now connected in parallel with the resistor capital R and the first capacitor. On figure 10.3, we need to draw a line to show the variation with time t of the potential difference V across the resistor. So in this case, we have connected an other capacitor in parallel with the first capacitor. So when two capacitors are connected in parallel, capacitance increases. So simply now we need to understand what is the effect of increasing capacitance on time constant of capacitor. So if capacitance increase, so time constant has to increase because R is constant. If tau increases, it means capacitor discharges slowly. So we can simply write down capacitor discharges slowly. And now if this point is clear to you, now simply we need to sketch a line, a curve on the previous curve. So let me show you how you can sketch in a nicer way. So this is how you can sketch. So you can see in this case, ripple, the variation in PD across resistor has been decreased. So now the ripple is only this much. So this is the ripple. And the previous ripple, let's use a different color. Ripple previously it was this big. Now the ripple has been decreased, means the variation in PD across resistor has been decreased by connecting another capacitor in parallel. If we connect in series, then C will decrease. Time constant will decrease, so ripple will increase. Very important one, how capacitor is connected. If capacitor is connected in parallel, it means tau increase, ripple will decrease. So let me write down here, this point is very important. If two capacitors are connected in parallel, so the ripple decreases, variation in PD decreases, this will decrease. If in series, ripple, the variation in PD, this will increase. So next time they can ask you about this one. And that's all for today's video. We have discussed some beautiful questions on AC and rectification, and if you go through past papers and you take all the questions about graph from this topic, you will see only these different types of graphs. So it simply means that we have covered all possible graphs about AC in today's lesson. If this video was helpful, please like and subscribe, because your encouragement is very important to make more videos. More encouragement, more videos. See you next video.